This lesson on compressive wave speed involves doing some hands-on exercises. I'm going to give you instructions during this lesson. I would like you to watch the video as an example of how to do the exercise. Then read your workbook and follow the instructions in the workbook to do the exercise using the WATHAM software. When simulating transients in pressurized pipe systems, it is critically important to be using the right compressive wave speeds in the pipes. This fact makes this subject something you need to understand well. Doing some exercises will make you familiar with calculating compressive wave speeds in pipes. If you've been following the slides in your workbook, great. Otherwise, now is the time to open up your workbooks to the section on pipe wave speed. Wiley and Street are in their book Fluid Transients in Systems, which you'll see listed in your workbook as reference number 6 at the end of the topic on pipe wave speed, present an excellent description of the factors that govern pipe wave speed. And the key factors are summarized in this slide. In your workbook, over 3 pages, is a distilled version of the wave speed theory presented by Wiley and Streeter. You can use those pages in the workbook or Wiley and Streeter's book as your guide to calculating wave speed. I'm going to let you explore that material at your own pace at another time. We're about to do an exercise using WATHAM, which applies these formulae. WATHAM versions 11 and above do these calculations for you. This lesson will show you how to make that happen. After watching this video, I need you to launch WATHAM using the shortcut on your desktop, do a file open, browse to the folder called Exercise 2 on your USB memory stick, open the model labeled peak at wavespeed.wdt. That model uses data for unplasticized PVC pipes, pressure class PN18. Your mission is described in the workbook at or near page 37. Your mission is to take the manufacturer's internal diameter and thickness data and type it into the table inside WATHAM for the UPVC PN18 pipe class. Manufacturer's data is available at about page 38 of your workbook. The workbook from page 37 to 39 gives a recipe for doing this under the paragraph heading How. First, watch me use the recipe in the workbook so you can see how to do the exercise. After watching this video, read the workbook, follow the recipe given in the workbook and complete the exercise. I have opened the file peak at wavespeed.wdt from the Exercise 2 folder. This model contains only 3 pipes. Let me turn on pipe labels. The sunken pipe, as its name suggests, is laid as a buried pipe. The second pipe is part of a treatment plant, and it is an example of exposed pipework constructed above ground. Lastly, the third pipe is laid directly on the surface of the ground. You would probably not snake a rigid polyvinyl chloride pipe over the ground, but this lesson is trying to demonstrate how to set up wave speeds for pipes. The mission is to add the nominal diameters and physical dimensions for UPVC class PN18, which will allow WATHAM to calculate the wave speeds for this pipe class. How can we do that? I will use the Options menu to select the job pipe library, making the pipe materials in my job pipe library appear on the left side of the map. I am interested in the unplasticized form of polyvinyl chloride, so I will select that material and click the Edit button. In the form, we can see the physical parameters, modulus of elasticity and Poisson's ratio, that the software needs to calculate wave speed of various sizes of pipe made out of this material. As a side note, When using the Colbert-White formula, it is the pipe material, or its lining, that governs the roughness height of all pipes made from this material. That is why that parameter is defined here as part of the material's specification. Also note, if you are adding a new pipe material to your pipe library, you can either enter these values manually or inherit values that the software already knows for some standard pipe materials, for example by making a selection from this list. Okay, so that is how data is defined for the pipe material, in this case UPVC. Now let's go looking for the PN18 pipe class for UPVC. Note the material polyvinyl chloride U is already expanded, and I discover that my pipe library does not yet have a PN18 class. To solve that, I simply create one and edit it. I select the polyvinyl chloride U and click the Add button up here to create a new pipe class. It appears down here. Just let me slide the tree wider to see the full label. Now I can select this new pipe class and click Edit to give it some values. A new pipe class is initialized with useless labeling and no information about nominal pipe diameters in the class. To fix that, start by giving the class a unique label. In this case, I know that PVC U-18 is what I want as a label. That's not used anywhere else. Now for a description, PN18 will do nicely. Over here, set the maximum working head as 180 meters. And the Series 2 Blue Brute catalogue is the source of the data I'm about to enter. It's our task to provide the data using manufacturer's catalogue. Looking at your workbook, page 38 I think, there is a copy of table 2.5.2 from the iPlex catalogue for Series 2 Blue Brute. The manufacturer makes only 5 nominal diameters in this PN18 class. To add these 5 nominal diameters and their dimensions, I click the Add a Row, or Add a New Row button, and enter the pipe's parameters. Just let me do that. Nominal diameter, 100. Outside diameter, 121.9. When I'm happy, I can click the OK button. Before I do that, what can we see in the table? As well as computing the pipe's internal diameters, their wave speed, also known as celerity, for the three cases of pipe laying constraints have been computed. Note the celerity values calculated for the three constraint conditions. What are the trends in celerity versus diameter? Depending on how pipe thickness changes with pipe diameter, in general the wave speed becomes slightly slower in larger pipes. Generally, the larger pipes are more flexible. I will click the OK button to stop editing the pipe class, and I will click the Close button up here to save these edits and close the pipe library. Yep, that message is fine. Okay, up to this point in the lesson, we have defined the parameters for a pipe material that influence wave speed, and we have specified the pipe dimensions, which also influence wave speed. One element remains to be specified, and that relates to how each individual pipe is installed or constrained. The laying condition of the pipe influences its wave speed. So let's move on and see where that aspect of the story is defined. Each of the pipes in the model has been previously defined as 100 mm UPVC Class 18 pipe. In addition, the software's current pipe type has been set as 100 mm UPVC Class 18 pipe. I'm in edit mode, and I'm going to right-click each pipe and select Edit Pipe. And I'm going to note each pipe's data for wave speed, laying condition and pipe type. And if necessary, make the pipe inherit its values from the pipe library for 100 mm UPVC Class 18 pipe. I don't need to do that because I see that is already the case. So I see I've got a wave speed for this pipe of 509 meters per second. Okay, moving on to the treatment plant pipe. Perhaps what I forgot to highlight in that previous pipe was that its laying condition was buried at cover. Whereas in the treatment plant, this pipe's laying condition is follow plant isometrics. Yes, it's 100 PVC and its wave speed is 483. So all that's changed is its constraint conditions. And looking at third pipe, its wave speed is 518 and its laying condition is lying on the surface. In the language of the software, pipe type 100 PVCU-18 means a 100 mm nominal diameter pipe in the UPVC PN18 pressure class. That is, nominal diameter followed by the user specified label for the pressure class. I spend too much of my professional life working with just one fluid, water. I almost forgot to talk about the fact that if you put a different fluid through these pipes, their wave speed will be different. The mass density of the fluid and its bulk modulus of compression influence wave speed. Let me show you where you define those two values in the software. In edit mode, we go to the global data tables and we click on the general tab. This is where you specify these two values. Summarizing the key points. Users specify the physical characteristics of the fluid and the pipe materials, plus the dimensions of pipes available within pipe classes. The software calculates wave speed and stores the results for all pipes and their various constraint conditions, that is, possible pipe laying conditions, in the pipe library. Users define each individual pipe's pipe type and its laying condition. The software selects each pipe's wave speed from the pipe library, matches it to the laying condition, and it is this value that is used in transient simulations. Thanks for watching. When you are ready, please watch the second part of the lesson, which looks at the influence of air entrained as bubbles in the fluid.